So now that you've seen what total internal reflection is, let's look at the explanation. Well, imagine we have water and a surface between water and air. And now we have a light source underwater and we send it towards the other direction. Well, the laws of refraction now tell you that there's two rays, of course the reflected ray and the refracted ray, and the refracted ray leaves at a particular angle. And when you go from the optically dense medium, i.e. water, into the not so dense medium air with a refractive index close to 1, then we get a bending away from the normal. And now the funny thing is, according to Snell's law, that there is one particular situation where the exit angle would be at 90 degrees from the normal. And then we have the trouble if we go at a ray that is even bigger than that. So this angle is called the critical angle. If we go beyond the critical angle, like you see here, when we have trouble, because there's no, according to Snell's law, there's no solution to the problem of a refracted ray. It cannot go anywhere. It cannot go beyond 90 degrees because then the sign of that angle would even go smaller again. So there's simply no solution. Well, or more precisely, you would get a complex valued solution, but that, of course, doesn't seem to make sense at first. And so the effect then is that all the energy of the light has to go into the reflected ray. So therefore we get what is called total internal reflection. Internal because we stay in that medium, that optically denser medium. And of course that's a very interesting and very important effect in practical optics. So where is it used, for example? Well, as you see here, it is used as total internal reflection in prisms to simply have a mirror of very high quality, because total internal reflection has very close to 100% efficiency if the optical surface is very flat, and so you're not losing any energy. And so this way you can redirect light, and that is used, for example, with what is called poroprisms in binoculars, and this allows you to displace the incoming rays from a point here to a point here, so that it allows you to have two effects. First of them, the first effect is you can actually tilt them with respect to each other, which allows you to control that distance, that allows you to set the interocular distance in such a binoculars. And the other thing is also it increases the distance of viewing, and therefore increases depth perception when you're looking at the scene through such a binocular. So here you see how binoculars look like. This is a very old example of binocular by Ernst Abbe, who lived 1840 to 1905. And you see the poroprisms are actually here and here. So it works like this. There's such a poroprism which bend the right ray twice, and here twice again it goes this direction. And then by changing this angle here, you can change this distance, which allows you to adjust the binoculars to your preferred distance between your eyes. So let's look at such a pair of poroprisms in the experiment.